Okay, in this video, we're going to do some weird, unique, or tricky FRQ parts. So these are things that my students the first time around when they were taking the exam came back and said they found tricky. Or every year when we're reviewing, students traditionally find these tricky as well. So it's kind of like a last second, you've done all your review and you just want to go back over a couple of weird things that you saw along the way. So hopefully this is helpful as you finish up your studying and you're getting ready for the exam. So I'm going to do some area volume things, then I'm going to do some differential equations things, then I'm going to do limit continuity differentiability things, related rates things, and then a bunch of random stuff at the end. I also made a separate video on using L'Hopital's rule on the FRQs because that's just a recent emphasis. So watch that video if you're looking for L'Hopital's stuff. I didn't do any of that in this one. All right, let's take a look at them. So I will be writing out the solutions, but really the idea is to just look at the problems, see how it's strange or different, and see the approach that we would take to deal with it. So in 2008, number 1D was kind of a unique area of a cross-section problem where you were told R is the region bounded by the graphs. The region R models the surface of a small pond, so that's weird. And at all points in R, a distance of x from the y-axis, the depth of the water is given by h of x, which is 3 minus x. Find the volume of water in the pond. So when I'm lost on these, I start drawing rectangles and rectangular prisms, and I'm not kidding about that. Any area of a cross-section problem that I'm not immediately sure about, I'm going to draw a rectangular prism and label it up. So the rectangle that I would draw is just kind of here, and based on that rectangle, right, the horizontal is dx, the vertical is top takeaway bottom. Now, how does this relate to this pond that they're describing? Well, the depth of it is h of x, so I'm going to draw this and say the depth is h of x. I have f of x minus g of x. I have dx. So really, I just need to multiply those to get volume and then integrate it to find the total. So this is what we ended up with, and you can work it out. So I'm going to try to create a playlist of all of the FRQs if I've done them. And I will link that below or maybe in a card above one of those, and hopefully I remember to do it. Next up, this is 2016 5B, so we're still doing an area volume thing. People just kind of freaked out about this. I think the reason people freaked out is that the picture that they gave you is a little deceptive depending on how you want to look at the function, right? So we are told that at height h, the radius of the funnel is given by r equals 1 over 20 quantity 3 plus h squared. So this was the funnel problem. Now everybody talks about the spinning toy problem. I look at them and they're the same problem. So we just want to find the volume of the funnel. I think what happened here is that people looked at the picture and they confused the independent and the dependent, and they thought they had to solve something for something else, and none of that was necessary. What I've done is I look at this and I say that r is a function of h. I sketch this. It doesn't even need to be accurate. I just need to get the idea. So I'm going around the h-axis. So my integral, when I set it up, pi from 0 to 10, because h goes 0 to 10, and then the quantity squared. Now what was weird, and I'm not going to do it in this video, but I definitely did it in another video, we had to do this whole thing by hand. So you have to square the whole thing out, reverse the power rule. But remember, this is a really good example, you don't need to simplify the numerical answer. So once you get down to using the fundamental theorem, you're going to sub in 10, sub in 0. Just leave it. Don't simplify it. Get your answer and move on. All right, let's look at the next one. 2021 3C. This I think this was a normal volume problem, but let me tell you, everybody freaked out about this. This was the one that everybody talked about. So a company designs a spinning toy. Y is cx square root of 4 minus x squared, which is kind of weird, but then in most of the parts, they just told you what to do with c. Let c be this, let c be this, solve whatever. Part C is the one that people, I don't know, maybe all the parts, but part C in particular. For another spinning toy, the volume is 2 pi cubic inches. What is the value of c? So we're going to rotate that curve around the x-axis, and then we're going to find the volume. So just set it up, right? So it's going to be pi, the integral from 0 to 2. You have to figure out 2 because the square root of 4 minus x squared. So x has to be 2 or negative 2, but looking at the picture, x is definitely 2. So pi, the integral from 0 to 2, quantity cx, radical 4 minus x squared, dx, and then the whole thing should equal 2 pi. Now we just have to solve for c. So it's a unique, different thing, and that's the point of the video. But it's not something you haven't done before. You've done volume problems, you've solved algebraic equations. same deal. So we kind of end up with this. And then, again, you had to solve this by hand because there's only 2 calculator questions. So a little annoying, but whatever. All right, let's take a look at the next one, which will be a differential equation type of thing. So this is 2007B. Now this is, we're going to find M and B. Remember, I'm doing like unique problems. There are a lot of typical things you would do with this. This is sort of unique. So we are told that y equals mx plus b is a solution to the differential equation, and we want to figure out M and B. All right, so I'm going to give you 2 different ways to do this. I'm not going to make you watch me solve it. The first method, y equals mx plus b is our solution. There's a y in the differential equation, so I'm going to literally replace that y with mx plus b, which gives me this. And then I can kind of factor that, so I have the coefficient of x, and I have the constant, and I put parentheses around the constant. Now, we also know that y is equal to mx plus b. So if y is equal to mx plus b, that means dy dx is also m plus 0x. I mean, it's really just dy dx is m, but since the other version has an x in it, I thought this version should as well. Since there is no x, I made it 0 x's. Now what I want to do is I just want to equate coefficients. So I've boxed them here. From this, I get 2 different equations. The first equation is 1/2 plus m is equal to 0, the things in the blue boxes. And then the other one is b minus 1 is equal to m, the stuff in the yellow boxes. And from there, we can solve for m and we can solve for b. I'm going to give you a different way you can solve this because this is a fairly common type of differential equation. So in the event that it looks like this and this works, you can do this. So here goes. I'm going to find the second derivative. Why am I doing that? Because y equals mx plus b has a second derivative that is 0, so I can use that. So here's my second derivative. Don't forget implicit, right? The derivative of y is dy dx. Then I had to sub for dy dx, 1/2 x plus y minus 1. Then I simplified that, so the second derivative is 1/2 x plus y minus 1/2. Now, if y equals mx plus b, which it does, then dy dx is m, the second derivative is 0, so this leads me to those 2 things must be equal. If those 2 things are equal, that means that y is equal to negative 1/2 x plus 1/2, or m is negative 1/2, b is positive 1/2. Either way. So that was a unique, different thing, right? That's the point of this video, is we're just picking out parts of different things that are unique or a little weird, or that generally speaking, my students have found difficult. So everything in this video is something that people found difficult. They're all good things to refresh your memory about right before the exam. Let's look at the next one. The next one actually, it's like literally the same problem. I mean, like, it's not exactly the same problem because the differential equation is different, but it's the exact same thing. So I'm not going to make you watch this. These are my 2 solutions to this. This is 2015 4D. So this is the advantage of doing as many FRQs as you can. You'll see the patterns, you'll notice it, and you probably will have solved most of the problems ahead of time. You just have to decide, how does the new problem fit into what you've already done. All right, the next thing we're going to do is we're going to look at limits, continuity, differentiability, strange problems. All right, 2009B 3A. So this isn't really a challenge. Well, I mean, maybe it is. It's not like a super hard problem. It's just that, like, it's uncommon. It doesn't come up a lot. So we have to use one-sided limits and the definition of the derivative. So that's a little weird. We're given the graph of f. We're asked to find if f is differentiable at x equals 0, and we are told we have to use the definition of the derivative and one-sided limits. So you have 2 different things you can do. You can do the limit as h approaches 0, but one-sided limits. So h approaches 0 from the left, h approaches 0 from the right. So let me show you that work. H approaches 0 from the right, we got f of 0 plus h minus f of 0 over h. That's going to be 2/3. You can just read that off the graph, right? Up 2 over 3. H approaches 0 from the right, f of 0 plus h minus f of 0 over h. You actually can't figure that out because we don't know what the graph is there, but we definitively know that that is definitely negative, right? That has a negative slope as you approach from the right. So the one-sided limits can't be equal because a positive can't equal a negative, and so not differentiable. You could also have used the other form of the derivative. The limit as x approaches 0 from the left, f of x minus f of 0 over x minus 0. Same exact idea, just wanted to put it down in case you were wondering, like, wait, can I? Yes, you can. All right, so for this one, you definitely need to know the limit definition of the derivative, right? It doesn't come up a lot on free response. It comes up a lot in the multiple choice when you're trying to match, like evaluate this limit, and the limit, you look at it and you're like, I don't know any technique that would work to evaluate this. And then you realize, like, oh, it's actually just the derivative of something. a very good way of finding derivatives. All right, the next one, same general-ish idea, 2011 6A. We're just using the definition of continuity, but if you don't know the definition of continuity, how are you going to do this problem, right? So the definition of continuity is the limit exists, the function exists, the limit equals the value of the function. If you could see me, I'm counting that off on my fingers, which I do all the time. So here, I'm just going to show you my work. I found the limit from the left, which was 1. I found the limit from the right, which was 1. And then I found the value of the function, which is also 1. So since I found those, I'm going to make this a long, annoying statement, which maybe in general you don't want to be doing, but on the AP exam, you do want to do because it's like the perfect solution. And you have 15 minutes per FRQ. You have time to write up perfect solutions if you know them. So why not, right? So since the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x, which means the limit exists, but we've covered that by saying this, equals f of 0, f of x is continuous at x equals 0. So this all came down to knowing the definition of continuity, and if you don't know it, you weren't going to be able to do it. So make sure you know this. So these are little things where it's like, it doesn't come up a lot, so maybe you haven't thought of it in a little bit, but it could come up and it's worth it, especially if you're going for like a high 5, right? I mean, I know you don't find out how high it is unless you get a perfect score, but it's still worth it. Like, go for the best score you can get. These are the little things that can get you a higher score. All right, next up, same kind of idea. It's limits, continuity, differentiability. Like, those are the 3 topics that I'm covering with this set, right? 2019 6D involved the Squeeze Theorem, and if 2020, I think we all know, wasn't really a normal year, if that had been a normal year, I was convinced that the AP exam would have this on it again. So I think at some point they're going to kind of like get back to it. So this one's a really good one to know. The function, and you were told so much information about this, the functions f, g, and h are twice differentiable. G of 2 equals h of 2 equals 4. We don't actually need this line stuff for this particular problem, which I think is good. So it's known that g of x is less than or equal to h of x between 1 and 3. So g of x is less than or equal to h of x. That's important. We also know that k is a function satisfying g is less than k is less than h. So if g and h are differentiable, then they're continuous, which means that we're going to know basically that k is also continuous, but our question here is like, is it? So we need the definition of continuity again. Limit exists, function exists, limit equals the value of the function. But here we have to do stuff to establish it. So we need the limit to exist. So what I've done is I've said g and h are differentiable, which means they're continuous, which means the limit as x approaches 2 of g of x is g of 2, which is 4. And then I did the same thing for h. Then I'm going to say, since g of x is less than k of x is less than or equal to h of x, the limits also follow that rule. That is the Squeeze Theorem. So you didn't need to mention the Squeeze Theorem by name to get all the points on this. And generally speaking, I don't think you will ever need to mention the Squeeze Theorem by name, but make sure you're aware of it. And that basically what I wrote there is the Squeeze Theorem. If a function is in between 2 other functions, and the 2 functions it's in between have the same limit, it must have the same limit. So now we know that the limit as x approaches 2 of k of x is 4. All right, we also needed to show that k of 2 exists and is a thing, right? But since g of x is less than or equal to k of x is less than or equal to h of x, we know that g of 2 is less than or equal to k of 2 is less than or equal to h of 2. Now, it's really important that g and h are differentiable and therefore continuous in this scenario, but I had already said that. If I hadn't ever said that, this wouldn't really need to be true because maybe there could be a removable discontinuity for k, and it could just like slip in between them without being defined. But it has to be true because they're continuous and k is always in between them. There's no room there for k to not exist. So we know k of 2 is 4. And then because we know the limit definition, the definition of continuity, I mean, it is a limit definition, but the definition of continuity, we know that k of x is continuous. So there's definitely been a recent emphasis on this whole differentiability implies continuity, and continuity implies the limit as x approaches c of f of x equals f of c. I would be on the lookout for that, especially with L'Hopital's problems. If you watch that video, you'll see I talk about it a lot. All right, next up, related rates types of things. There are literally 2 related rates parts that I think of when I think of weird related rates problems. The first one is 2007B 3C. So this I'm saying is related rates or the chain rule, because it's really kind of a chain rule problem in my mind. So we have this wind chill thing. It's W of V 55.6 minus 22.1 V to the 0.16, which is annoying. Question C says, over the interval 0 to 4, the air temperature is 32. That's just necessary for the problem. At t equals 0, the wind velocity is 20. The wind velocity increases at a constant rate of 5 miles per hour per hour. So that's the rate of change of the wind velocity, or dv dt. What is the rate of change of the wind chill with respect to time, right? So these types of problems, you got to really focus in on like what's what. So wind chill is a function of v, and we are asked for wind chill with respect to time, not with respect to velocity. So we are looking for dw dt. So what I would do is write down this chain rule. dw dt is dw dv times dv dt. Now the question becomes, what am I plugging in, right? Like what is v when t is equal to 3? And what is dw dv, right? So, and dv dt we already know is 5 because it was given. But so at t equals 0, velocity is 20, and we're increasing 5 miles per hour. So we can actually work it out. We can say, at t equals 3, v is going to be 20 plus 3 times 5, because every hour you just gain 5, so 35. So the problem we're really doing here is we're going to do w prime of 35, right? 35 is velocity, so we can plug that into the derivative of w. So w prime of 35 times dv dt, which is 5, gives us this. This particular problem, there's another way that we can solve it. So the way that we can solve it is, because we know that v is 20 and then adding 5 per hour, we can say that v is just 20 plus 5t, which means we can completely rewrite w as a function of t and then just find dw dt. This is a really good one to take a look at. Highly recommended. I like it, but I like it because it's like a weird problem. So generally speaking, any problem that I really like is a weird problem, because otherwise they're just the normal ones that we do all the time. All right. Basically the same problem in my mind was 2008B 2B, and again it's like related rates / chain rule. So what do we know in this one? We are trying to find R of t is speed in kilometers per hour at which a car travels along a straight road. The number of liters of gasoline used by the car to travel x kilometers is modeled by g of x, which is given, whatever. X kilometers, that's liters. Now the question is, what's the rate of change with respect to time of the number of liters of gasoline? Well, g is the function that tells you liters, but g is a function of kilometers, right? So we're looking for dg dt. So I'm going to chain rule it. I'm going to say dg dt is dg dx because g is a function of x. And then what do I need to multiply that by to get dg dt? It would have to be dx dt. So the chain rule really helps you solve these related rates types things. But now I need to know what is x when t is 2. I think we actually probably did this. We did this in part A if we had done part A. So I'm just going to go through it. So this is the speed, kilometers per hour. Integrate kilometers per hour gives you kilometers. So x of 2 is going to be 206.370. And then we also need to answer what is dx dt, right? Well, dx dt is, if you look at above, we could have rewritten it as x of t is the integral from 0 to t of r of u du or something. Dx dt is just r of t, right? Kilometers per hour. And now we just have to multiply these. So dg dt at t equals 2 is g prime of that value times r of 2, which actually just works out to exactly 6, I think, which is amazing. But anyway, those are the related rates type of questions. So now we're going to hit like the random ones. And I'm just going to like point out things that I think are interesting about them, or, give you some tips on how to deal with generally strange problems on the exam. So the first one is going to be 2009, parts 2 and C, number 2, parts C and D, and also like A. You needed A to like really answer the question. But the point of this one is, the less familiar a concept is, the longer the problem will probably be, because they just explain the entire thing to you. Like, look at part C. It's insane. The final question for part C is basically w prime is 2 minus t times r of t. find w of 2 minus w of 1, right? So that's just going to be the integral of w prime of t from 1 to 2. That's all they wanted you to do. But they're explaining some things to you, right? So they're saying the function w models the total wait time for all people who enter the auditorium before time t. That's important for the next thing. And then when they ask you to find w of 2 minus w of 1, they tell you it is the total wait time for those who entered the auditorium after t equals 1. Okay, so now the question in D is, on average, how long does a person wait in the auditorium for the concert to begin? Consider all the people who entered the auditorium, which is actually the answer to part A if you did the whole problem, and use the model for wait time from part C. So that's what I'm trying to get at here. They're telling you how to do it. That's why it's a big, long, scary problem. And usually these are actually a little easier than other problems because they have to tell you exactly what to do. So we need basically the total wait time divided by the total people. So the total wait time would be calculated from when the door opens at 0 to when it closes at 2. So that's going to just be the integral from 0 to 2 of w prime of t dt. And then if you need the total people, you just want to integrate r of t from 0 to 2 because r of t is people per hour. So that's how we would do it. I just wanted to point out the general idea that the questions themselves are kind of linked together, and if you don't know how to do one part, one other part might be telling you how to do it. This next one I think is a good example of that. So this is 2009 3A, and the question people usually have is, why is 3A an integral? Well, my answer to why 3A is an integral, we're going to try to find the profit on the sale of a 25-meter cable. Well, what's happening here, right? So we know that the cable sells for $120 per meter, and we know that the cost to produce a portion of a cable that is X meters from the beginning of the cable is 6 root X dollars per meter. This is really a rate in, rate out problem, so you want to do a lot of practice so that when you get to this, you're just like, yes, I know what's going on. This is rate in, rate out. So what I want to do is I just want to integrate the rate in, which would be the money you're taking in, minus the rate out, which is the cost, right? And they actually tell you that. Profit is defined to be the difference between the amount of money received and the company's cost. That's what they're telling you parenthetically there in the note. So we're going to end up with this. The integral from 0 to 25 of the quantity 120 minus 6 root x dx. So some people are confused and they're like, why can't I just plug in 25, I guess, to find the profit? I don't know why people think they can do that exactly, but I would say in calculus, we generally are going to be integrating rates, which usually have a variable, but they don't even need to, right? That 120 doesn't have a variable in it. We're still integrating it. We integrate rates to find total things, and I think some people got a little lost on that. But the other thing I would say about this is that if you look at part B, it's asking you to explain the meaning of the integral from 25 to 30 of 6 root x. So if you wrote down in part A just, I think what most people did was like 120 times 25 minus 6 root 25, and they thought that that was somehow going to be right. So once you do part B and you're explaining the meaning of the integral from 25 to 30 of 6 root x, you should reconsider your answer to part A. Like, did it make sense in the context of having actually explained that integral? So go back, look at the parts. It's all related while you're taking the test. All right, next up. 2010 1C. Every year, people kind of either over or underthink this. I think people underthink this problem. So in this problem, we have snow is falling from midnight to 9 a.m., and it accumulates at a rate of f of t. That's not relevant to what we're going to do. And then somebody starts shoveling at 6, right? So they don't shovel at all until 6. So there's no snow removed until 6. And then g of t is the rate at which she removes snow from the driveway. And we're given g of t, and it's piecewise. So question C is, let h of t represent the total amount of snow in cubic feet that Janet has removed from the driveway at time t hours after midnight. Express h as a piecewise defined function with domain 0 to 9. All right, here is the answer. Now, the things that people screw up are the things that I have put in parentheses. So between 0 and 6, she removes nothing, so the function is just 0 between 0 and 6. Now, between 6 and 7, the rate of change is 125, but it needs to only apply between 6 and 7, so we have to offset and do t minus 6. So people forgot that a lot. A lot of people just did 125t, but that doesn't really make sense because 125t just plug in 6 and plug in 7 and think about how much snow you're claiming she removed. It's like way too much. Now the 125 in yellow, people forgot that by the time we hit 7, she has removed 125 cubic feet of snow. So it's 125 that's been removed, plus her rate of change is 108. And this is only valid from 7 to 9, so we do the quantity t minus 7. So a lot of people kind of struggle with that one. I would like to point out that if you graph g of t, you can kind of, thinking of integrals, work out what should be happening here, right? Between 0 and 6, there is nothing, right? Integral of g of t from 0 to 6 is 0 for sure. From 6 to 7, you definitely get 125. So between 0 and 7, she's only removed 125 cubic feet. Like, that's what I'm trying to get at there. So don't overthink it, but also don't underthink it. There's almost no way that the answer to this would have been 0, 125 times t, and 108 times t. I just think that, in the course of doing the exam, you should think, that seems a little too simple, and rethink it. All right, next up, we're just doing random things at this point. 2010 5C. I would say that adding a line can help. So when you're given a graph, sometimes you have to add something to the graph for you to really be able to visually see what's going on. So the function g is defined and differentiable on the interval from -7 to 5, satisfies g of 0 equals 5. The graph of y equals g prime, the derivative of g is shown. So we have the graph of g prime. Now, in part C, we defined a function h, which is g of x minus 1/2 x squared. We want to find the x coordinate of a critical point and then classify them. So I'm not going to actually do that. I'm just going to go through the logic of what I would do. So I know that h prime is g prime minus x, and for critical points here, I would need h prime to equal 0, which means I need g prime to equal x. Now, at that point, you're like, how do I even do this? Well, y equals x is a line, so I can just add that to my graph. And once I've added that, now it just becomes a question of what relationship between that line and the graph of g prime would mean that h prime is positive versus negative. So what I usually do is I just rewrite it. H prime greater than 0 would mean g prime is greater than x, or the graph of g prime is above the graph of y equals x. So that's going to be this entire interval. So we know that h prime is positive there, and then therefore negative here. So I'm not going to finish the problem, but it looks to me like root 2 is a critical point. It looks like h prime changes from positive to negative, so is a relative maximum. It also looks like 3 is a critical point, but there's no sign change in h prime there, so it's not a max or a min. But I didn't solve it in the video. All right, next up is 2011 1D. And again, if they're explaining a lot, it means they're telling you what to do. So this is a really similar idea, but I thought it was important because the thing they're explaining here is really useful. They're telling you were originally given S prime. Like, it kind of doesn't matter the context, but you can pause and read the whole question if you want. You're given S prime. They're telling you there's another thing, M, right? And then the height M is measured in whatever. Let d of t equal m prime minus s prime. Apply the intermediate value theorem to justify that there exists a time t between 0 and 60 at which the heights of water in the two cans are changing at the same rate. So they're telling you exactly what to do. They're saying define this d of t thing and then use the intermediate value theorem on it. So this is great because this is a template that we can use in future problems. And this idea has come up in future problems. I think this is a solution that you should almost kind of memorize. So what I do, d is continuous, and then just evaluate it at the endpoints. D of 0 is less than 0, d of 60 is greater than 0. So since d of 0 is less than 0 is less than d of 60, by IVT, d of t equals 0 for some t. Now, why does that mean that m prime equals s prime? Well, it's because m prime minus s prime is d of t. So m prime minus s prime is 0, which means m prime equals s prime, which means there is a time the rates are the same. I think that this is like a really good, simple way of showing that things are equal, and they've told us how to do it, so we should remember that and use it in the future. All right, let's look at the next one. This is 2017, number 2, and really the only thing here is look for sure at where the rates apply. So this is 2017, it's like fairly recent. They didn't really do this in the past. These two rates don't apply on the same interval. So this is a rate in, rate out problem. But for the first one, which is the rate in, it's applying between 0 and 12. For the second one, the first one is the rate out. I just didn't read. The second one is the rate in. It only applies from 3 to 12. So for example, in part D, where they say how many pounds of bananas are on display at time t equals 8, well, there's 50 to start with, but then the rate in only applies from 3 to 8, whereas the rate out applies from 0 to 8. You got to be on the lookout for that. Next up, I mean, we're getting down to it here. There's only a couple more that I wanted to talk about. If you've watched all the way through, like, amazing, thank you. 2017 number 6, there's nothing to even do here. I just was amazed. Look at all the different representations, right? We have G, which is a table. We have H, which is a graph. And we have F, which is given just as a function. So that's a lot of stuff. So G, H, and F, it opens the door for them to ask all kinds of questions within the same question, which I think is good. It makes the test a little less predictable, which, I don't know, it's probably good for the test. It's like worse for us, but still a good idea. So be on the lookout for that. Don't be afraid when you see it. Next up, 2018 3D. My advice here is to just be confident in what you know. So there's nothing really weird going on in this problem. It's just that you're given the graph of G, which is a continuous function, and is the derivative of F, right? So G is the derivative of F. And then the question is, find the x-coordinate of each point of inflection of the graph of F and give a reason for your answer. People freaked out in 2018 about what are these weird, like, horizontal to non-horizontal things doing. Well, you don't have a sign change there, right? G is not going from increasing to decreasing. It's going from just constant to increasing, and then constant to increasing, and then constant to decreasing. None of those are a sign change in the second derivative. So just be confident in what you know. At x equals 4, f of x does have a point of inflection because f prime, which is g of x, has a relative minimum. If you know what you're doing, just do it. When you run into a strange scenario, be confident that what you know is the correct thing. All right, I got 2 more. 2019 1C. I only know that this is weird because I got a lot of comments on it when I made my solution video. So you got to know your options for things. This is a question basically saying, you know the rate in and you know the rate out. So E is the rate in, L is the rate out. At what time is the greatest number of fish in the lake, right? So your options are either the candidates test or the lonely critical point theorem, which not everyone seems to know. That basically says if there's one critical point and it is a maximum or a minimum, then it is also the absolute maximum or minimum. So that's basically that theorem. So here's your work. If they're asking for time alone, just time, not the value, you're probably actually going to be using the lonely critical point theorem. Like that's not 100%, but it's like very common. When they only ask for time and they don't ask for amount, there's almost certainly only going to be one critical point, and at that critical point, it does what you want it to. If there's more than one critical point, you cannot use the lonely critical point theorem because it's not a lonely critical point. There's more than one. Then you're doing candidates for sure. This is the work that I did. You can, read it and pause, or you can go watch the whole video for this. I went really deep into this idea of the candidates test versus the lonely, or really the only critical point theorem, but I always call it the lonely critical point theorem, in a video about maximums and minimums, which I'll either link above or below if I remember to. Just wanted you to be aware that you don't always have to do the candidates test. And sometimes if finding the values of the function is hard, maybe don't find them. Maybe find another way to justify it. So in this case, I have justified it that way. Pause it and read it if you're not familiar. Hopefully you're familiar. All right, the next one, which is the last one I want to talk about because we're in the 2021 things and that's the last year I have available. 2021 2B was just a weird question. It's not a weird question if you're in Calc BC where you've had to do this with like polar before or parametrics, but I don't remember this being in Calc AB before. So what we have is 2 particles. And in question B, we are just asked, are the particles P and Q moving toward each other or away from each other at t equals 1? Explain your reasoning. So the thing that I think was a little tricky about this, and it really wasn't, but it could have been, is that we need to know P and Q relative to each other before we decide if they're moving toward or away from each other. So consider their relative positions. This is only here because it's like a new type of problem that I think hasn't been on it a lot. So from part A, we had to figure out where we were at 1. So P is at 5.371 and Q is at 8.564. I need to know velocities to actually solve this. So the velocity of P is 0.841. The velocity of Q is like exactly -1, which is unnerving, but go with it. So what I've done is I just make a picture, right? So P is to the left, Q is to the right. P is moving to the right, Q is moving to the left. You can see in this picture now, they're definitely moving toward each other, but I have to write it up. So here's my write-up. It's nothing groundbreaking, but it is a little weird and you do have to think about it. P is on the left of Q, P is moving to the right, Q is moving to the left, the particles are moving toward each other. That's all that's really required after you've listed out like the positions and the velocities. So my advice here is really just like, don't be afraid of a twist question. Just think it through. You definitely know the calculus. You just have to decide how that calculus applies to this new unique question that you're facing. So those were the unique, weird, kind of tricky parts of FRQs. I hope somebody finds this useful. I didn't really know how to do this whole video. So anyway, I hope you found this helpful and good luck.